Thank you, Marike, for the introduction. Welcome everyone to the May webinar on data conditioning. Without further ado, let's get started. Today we will look at some introduction first of all. Why would we want to do data conditioning? Then we will talk about both open source methods and advanced methods that require plugins. Next we will talk a little bit about resources, what you can access to kind of learn more about data conditioning in Opendetect. Then we will have a little recap and then open up for questions and answers. So first of all, introductions. There is indeed something for everyone in the realm of data conditioning. Today the focus is on post-stack tools. So we will look at both free tools in the open source version of Opendetect as well as tools that require commercial plugins. One thing to keep in mind is that data conditioning is highly task dependent, so dependent on what you want to do, whether it be enhance your data to find a bright spot or flat spot, or simply remove noise to better track horizons, for example. These two you can approach differently. We will also look at both tried and tested data conditioning methods as well as the more recent machine learning tools. I have some real-life examples from a few datasets in Opendetect that I have prepared. So why would we bother with data conditioning? As mentioned here, it can help with interpretation of your data. It can help you see beyond the original raw volumes. And we need to approach this so that we do data conditioning fit for the task. Are we just looking at enhancing the signal to noise ratio, or are we looking at enhancing geologic features such as flat spots? And we need to keep in mind that noise is also signal. Perhaps it is signal that we don't understand. And finally, for certain tasks, really this garbage in, garbage out holds true. You need to make sure that you do everything you can in order to condition your data before you start with your actual interpretation work. Otherwise, that work might also not look very good. So you can think of it in the simplest terms as if you're tracking a horizon on very noisy data, your horizon, first of all, will not be able to auto-track very well in this volume. And second of all, you will end up with a very spiky horizon in the end. So one thing to keep in mind. Now let's dig into the open source methods in Opendetect. One thing you may want to start with is analyzing the amplitude spectrum of your data. So in this example here from the Delft dataset onshore Netherlands, I've extracted the amplitude spectrum for the whole section. We can see that we have something going on here under 10 Hertz that I may or may not trust. Similarly here above, say 80 Hertz, there is a little spike here in the high frequency, which is something that I'm a little suspicious about. One thing you can do when extracting amplitude spectrums is really focusing on the interval of interest and then extracting this amplitude spectrum again. So here you can see if we narrow the window, we can again extract the amplitude spectrum, and we see that we're getting rid of that high frequency bump that we saw in the previous slide. There is still something going on here below 10-15 Hertz that I may want to filter out. So something to keep in mind here as well. This is a good starting point. We can apply median and average statistical filters. It is our tried and tested dip-steered median filtering method without the steering. So as long as we keep in mind that we don't go crazy on the step outs, and perhaps also avoid high dipping areas if possible, we can indeed run statistical filters as well, simply along z-slices. Average filters are available as well, but here it is important to keep in mind again what these two actually mean. So median is inherently edge preserving, whereas an average averages out all the different values in your data. So if we look at this here to the right from kind of a map view where we have our different sample points. If we take the central sample, we apply a inline crossline step out of 1 in each direction. We then replace the median or average value from these to this sample that we're looking at here in red. If we increase this to 2 by 2, we're taking the median or average values of 2 samples that are neighboring this central sample and replacing that value with that instead. Convolve is another powerful tool that is available in the open source version of Opendetect. Here in this example, I'm showing you perhaps what's a better approach to filtering high dip areas instead of using a median or average statistical filter along a z-slice would be the convolve attribute. Here I'm simply doing a low pass convolve attribute, and you can see here compared the left image to the right image here. Then we have a number of other tools if we're looking at enhancing single geologic features such as flat spots. Here I found an example of something that could be a flat spot. We can use optical stack. Here I am displaying 10 inlines together, the average values together on this line to enhance or see these flat spots better. We have other attributes such as texture, which is a GLCM type of attribute, or we can simply do AGC, auto gain control correction on the whole data set to sort of get rid of the internal variance in the reflectivity. Let's now go into Opendetect and look at some open source examples. So here we are in Opendetect. I have the F3 demo and we're looking at just the original Seismic, and I wanted to show you what a median filter may look like when we do not use steering. So let's open up our attribute set here, 3D, and I will browse to our volume statistics attribute. A dip steer median filter you can already access in the list of attributes. It is a separate entry here. In our case, we will not do the dip steer median filter, but just a simple median filter. So I will do this through the volume statistics attribute instead. We will select our input data, which should be our original Seismic. We want a flat time gate so that we flatten along the z-slice, not vertically. We do not know the step out. We will actually evaluate that in just a second. And our output statistic we want is median being edge preserving, and we can call this median filtered Seismic. We add as new, and then I want to evaluate my step outs. So let's click on the evaluate button here, and we want to evaluate our step out. We start with a 0, 0, and add 1 inline and 1 crossline for each slice that we're gonna calculate here. So this is going to pre-calculate all of these realizations into my computer's memory, so I can then on the fly use this movie style slider here to have a look at the results in real time. So here we have a 0, 0 filter, and then once I slide this toward the right, we're adding 1 inline, 1 crossline, and we're calculating the median value. And you can see what happens if I go too far. If I over smooth this, you can really start seeing that we are indeed taking the median value along a z-slice. Everything becomes flat. So we want to stay away from the high step outs. We want to have something like a 1 by 1 or a 2 by 2 in this instance, and then hit accept once we've decided on a good value. That will then give us the settings for this attribute. If I want to QC this attribute further, I can do so by doing mathematics, and I will do Seismic, original minus smooth, and I will set my original as my original Seismic and my smooth as my attribute, which is median filtered Seismic. We call this residue. and we add as new. And I can then view this on this inline here by loading the residue attribute on here and scaling this to similarly to what we had with the seismic. We see that this is mostly incoherent. We do not see any structure here, so this is pretty valid, right? Another filter I wanted to show you that is included in the open source free part of Opendetect would be the convolve, where we can do fairly fancy low pass filter simply by choosing convolve. We want the original seismic. We want a low pass smoothing filter. In this case, I know that there is some low frequency noise here that I want to get rid of. We choose a filter size, a shape, and then we add this, add as new. And if you wanted to, you could also here evaluate this filter size, but I can simply go ahead and QC this one by adding this attribute onto this inline. And we can then see that it also does a pretty good job of getting rid of the incoherent noise. It also does something of a normalization of the amplitudes. You see that it takes away a bit of the strong peaks and troughs. So it's a little different filter in that sense. Let's get back to the presentation. We'll be looking at additional open source tools and commercial applications. Let me show you then a few other open source tools that we do not have time to go over due to the time constraint of this webinar, but we also offer a local velocity fan filter. It is a 3D filter to suppress energies with apparent velocities in time surveys or apparent dips in depth surveys. It's, for example, useful for suppressing flat multiples that are obscuring the actual dips. We offer a delta match, delta resample to align angle stacks or 4D volumes. You could also do matching filters in the wavelet manager to equalize seismic from different vintages. Tried and tested bandpass filter is of course available, gives you a bit more control than the simple convolve attribute I showed you. We also offer a grubs filter, and to take a look at all of these attributes that we offer, I would encourage you to visit the web page and browse to our attribute table. This attribute table offers a list of all attributes that are available in Opendetect. They are sorted by being amplitude-based, frequency-based, multi-trace attributes, impedance-based, dip and azimuth-based, processing and filters. Then we offer some information on meta-attributes, horizon cube and SSIS-based attributes, and pre-stack attributes. And all of these will have clickable references and also a link to the relevant documentation of that particular attribute. So let's then take a look at some advanced methods that we have available in Opendetect that would be utilizing commercial plugins. We can do the dip-steered median filter, which is again a volume statistic attribute, this time with the dip steering. So instead of looking along the z-slices, we would actually be following the dip and azimuth of the seismic reflectors to compute our median values. We have an edge preserving filter that comes as part of the faults and fractures plugin that allows you to create volumes that are smooth but have a sharp kind of fault scar. The fault enhancement filter is a little bit similar, but this one only requires the dip steering plugin. This one is a combination of two different filters, the dip steered median filter and a dip steered diffusion filter. So wherever we have highly similar seismic, we use the smooth volume, and where we have faults or low similarities, we use a diffusion filter, which also sharpens those fault edges. Then we have Seismic Spectral Bluing, which is a plugin from ArcCLS, which allows you to enhance the vertical resolution using well data. We have footprint removal and destriping from Estimages, These two here deserve, I think, their own webinar, so I will leave these to another time. Then we also have a number of machine learning tools that have come out more recently. We support Keras TensorFlow, PyTorch, and scikit-learn. And the examples from the machine learning tools I wanted to show today is a pre-trained model from Lundin Geolab in Norway, now part of Aker BP. So let's look at these a little bit more closely. So dipsteer median filter, as we've seen, is a volume statistics attribute. We can evaluate and QC the step out to make sure that we're not removing actual data. So as we saw in the demo with the median filter without the dip steering, that is also possible to do. In this case, we are actually utilizing the steering as well. We get a result like this, and then we can also compute the residue to see what was actually removed. So here we can see that this is mostly incoherent, so we should be good to go. Another filter type I mentioned here was edge preserving smoother and the fault enhancement filter. This is again a part of the dip steering plugin. That would be the fault enhancement filter, and the faults and fractures plugin, which brings you the edge preserving smoother. As mentioned, the fault enhancement filter is a combination of two filters, the dip steered median filter and the dip steered diffusion filter. The edge preserving smoother, on the other hand, uses fault likelihood, and where we have faults, we sharpen those, and where we have just good seismic, we smooth it out. So here's an example of the fault enhancement filter, and here is an example of the edge preserving smoother. I wanted to give a special mention here to a few attributes and a few plugins that we will not have time to look at today due to our time constraint. Again, we have Wayne Moggs plugins that are available. We have a recursive Gaussian filter that is part of Opendetect Pro in the Volume Builder tool. There is a Fluid Contact Finder plugin that is designed to do just that, enhance fluid contacts, and a frequency shaping and post-deghost tool. So let's now head into Opendetect and take a look at some advanced methods in more detail. So here we are back in Opendetect and our F3 demo. Let's open up our attributes set again now to take a look at the fault enhancement filter. It is actually a default attribute available in the default attribute sets. We can open it up, either the expert mode, which gives you a little bit more control, or simply the simple mode here, where we simply have to give it a input volume. We select our original seismic, and we need a steering volume. So once we've selected the seismic volume and the steering volume, we hit OK. And all we need to do is then determine what value we want to use as a threshold to use one or the other volume. So you can see here that if our similarity is above a certain value, we will then replace the dip steer diffusion filter with our dip steered median filter volume. So here we want to use the dip steered median filter for the smooth volume and dip steered diffusion filter for the DSDF. We give it a name, and we can now evaluate this constant. So we click again on the evaluate attribute, and we want to evaluate our constant. We can start with 0.1. We do increments of 0.1, and we will do 9 steps. So we'll go from 0.1 to 0.9, and we let this calculate. Now once this has calculated, we can then view our results and we can evaluate our constant. So you can see what happens if I zoom in here on an area with lots of faults. We have everything now using the smoothed filter, and if I move this toward the right, we introduce more and more of the diffusion filter. So indeed a 0.6, 0.7 looks to be pretty good. We accept that, and we have our fault enhancement filter result. For our edge preserving smoother, we need to go into our faults and fractures plugin here. And under filters, we will find a number of filters. Also, this fault enhancement filter is here. The edge preserving smoother is what we'll select. We say go. In essence, what we give here is the input seismic, and we can give it an output name if we do not want to do anything with the advanced settings. The advanced settings allows us to change some things that go under the hood here, such as the fault strike scan, fault dip scan in degrees, because we need to compute the fault likelihood here under the hood. The only thing here that is sort of critical is if you have faults that are dipping very steeply or very low angle, you can adjust these numbers here. We will simply click run here, and it will start a batch process, which does a number of things. I have actually pre-computed this, so we don't need to wait for this batch process to finish. But once this would finish, we would then get the result that may look something like this, right? So here we see that we get a smooth result where we have high similarities and a very sharp contrast here in the fault scarps. A final thing I wanted to demonstrate to you guys is the pre-trained models from our machine learning plugin. So we simply open up the machine learning interface, and we will go to pre-trained models, where we can select the Lundin Geolab Ajax. This is a kind of a brute smoother, does not preserve amplitudes. We simply smooth out everything. A less dramatic option is to use the simple denoise, but we can have a look at both of these and see how they compare. From Lundin Geolab, we also have a multiple removal tool and a desmile tool if you just simply wanted to remove the smiles from your post-tech seismic without going into velocities and all that. Those are also available. The idea with the pre-trained models is that they have been trained on actual data. We can simply click go. We only need to set our input data and an output volume, and we should be good to go. Here we will simply select our input volume, original seismic. We can adjust here the amount of overlap we want and a merge mode. I will only go ahead and reduce the amount of inlines to compute here to speed things up. We will call this Ajax version 3 and use GPU if possible. It speeds things up considerably. We click run and it launches a batch process window, and we simply have to wait for this to finish, and we can take a look at the result. And once this batch process window states that it has finished batch processing, we can go ahead and close, and we can view our result here on the inline. So I stored this as Ajax version 3. And as you can see, it has really done kind of a heavy smoothing here. This volume would be great for things like picking horizons. If we want a little bit less dramatic smoothing, we can simply go with these Lundin Geolab simple denoise. Again, click go. We need to give it our original seismic as input. I will again reduce the number of inlines here just to speed things up. And we will give it a name, simple denoise. And again, predict using GPU and hit run, and it will start another batch process window. Like this. We can then go ahead and compare these two by adding this one as well on the same inline. Simple denoise. And we can then compare these two and see that the simple denoise actually brings a result that is comparable to a dip steer median filter, a little bit less smoothing compared to the Ajax. And let's head back to the presentation for a recap. So let's look at the recap of the webinar, but first let's talk a little bit about resources available to you to learn more about data conditioning. There is of course user documentation and plugin documentation. We have the F3 demo tutorial that takes you through a number of exercises related to data conditioning. We also offer in-person training in Sugarland. We offer plugin training every third Tuesday of the month. Every second Tuesday of the month is reserved for our introduction class. Currently we have a rotating theme. Every other month we do machine learning, and the other months we take care of data conditioning. And you can sign up online on our Opendetect Pro Store. The topics that we go over during our data conditioning training you can see here. We go over some of the exercises that I showed you in the demonstrations just now. It is a full day from 9 a.m. to about 5 p.m. at our office here in Sugarland. So I hope to see as many of you as possible here in our office in the future. Now let's recap. So data conditioning is highly task dependent. It can be done both with open source and commercial tools. And we need to keep in mind also to use that evaluate attribute option there when possible, so that we can do a quick visual QC of what we're doing, so that we're not removing actual data. And I would then like to thank you for your time and open up for questions and answers.